Okay, when we get into class, we will redesign. Remember we did sequential search using global variables? We're going to rewrite this one so that we're going to get rid of those global variables. Instead of using those, we're going to pass parameters on the stack. So we'll do that in class. This one's a really good example, and I'll have handouts for you on this so that we can walk through it together. Now it's time for us to go back to Chapter 6. And I say back to 6.2. We're going to cover 6.2, but for recursion, which is the rest of what's in Chapter 6, we're going to actually wait on that until we get to the end of the semester, because we're going to combine what Chapter 6 deals with in recursion with what we're doing in mixed mode programming. Okay? All right. So, what are we going to do if we're calling an assembly language function from another piece of assembly language code? And the key is we've got to establish our own calling convention. So we've got to have a calling convention. Easiest thing to do, we've seen what the calling convention we've been using does. It's actually a pretty smart idea, so what we'll do is we'll mimic it for the most part, okay? Because we have to come up with our own calling conventions. We have to take care of all the things that C++ did for us via its calling convention when we called an assembly language function from high-level language, in C++ in our case. So, first thing, okay, we need to have a function declaration. So where do we put the code for a procedure? Well, a couple of things. So in C++, I can put the code for a function definition either above the main or below the main. In either of these two cases, it's going to be stored in the same file. Or I can put a function prototype in the calling code that has the main function and store the function definition in a separate implementation file. I can do the same thing in assembly language. In fact, we've been using a couple of assembly language programs in exactly this way. We'll look at those: io.asm, io.h. One is a header file, one is the definitions. Okay? So, here's the deal. Where do we put the code for a procedure definition? It is always going to follow a code directive. Okay? So, either in the calling code or in a separately stored file, it's going to follow or be part of a code segment. Okay? It's always going to be bracketed by proc and end procedure. Okay? Because it is a procedure. Okay? Then we're going to add an attribute. It is near 32. We're going to add this attribute to indicate that this code is in the same code segment as the calling code and that 32-bit addresses are being used. Okay, so how do we do this? In what sequence, and what is it going to look like? Okay, well, to answer those questions, let's look at some code that's going to initialize an array to 0. Okay, pretty simple. So we'll take a look at it. And what this is doing, let's start at the top because I've got a new directive I want to show you. EQU is a way to declare a constant. So I am saying I want max this identifier to be equivalent to the decimal value 10. So anywhere I use max in the code, I want that to be seen as the immediate value 10. Okay? Stack, I allocate my stack. I've got my data segment here. I've initialized my array to all -1s. Got to initialize it to something. So we've got all -1s there. And remember we said, it's got to follow a code directive. So here, I'm marking the beginning of a procedure. I'm indicating it's in the same calling or code segment as my calling code, and it's using 32-bit address defaults. Okay? And down here, this is the name of the procedure, and here's the end of the procedure. So this just brackets that function definition or procedure definition in our case. So here what we're doing is we're going to establish a pointer to my array, I'm going to establish a countdown counter, check it if it's 0. I'm going to move 0 into what EBX is pointing at, and then I can move my pointer to the next value, decrement my countdown counter, and if it's not 0, go back to the top. Okay? So all this does is it's going to take this array and initialize it to all zeros. When we're done, we'll return to whatever called it. So you say, well, what called it? Aha! Well, what called it is this. Remember, in C++, the first thing that the operating system calls is the main function in any C++ code. So the same thing happens in any language, and we can indicate where we want the starting point to be when we link and load this code. So here we indicate that we want to start execution at this label, start. First thing start's going to do is it's going to call this function. Okay? Now, let me talk about call. Call is another new instruction. What this is going to do is it's going to do part of what we saw in the 5 steps of the C++ calling convention. In particular, we said after it establishes a function prolog, and then it pushes parameters in reverse order, we said then it's going to copy the return address on the stack to the top of the stack and move the function name into EIP. That is what call does. Call is another complex instruction. It's going to copy the return address to EIP. Okay? Well, no, it's not. Sorry. Let me back up. It's going to, it's going to push the return address, and in this case it's going to push EIP to the top of the stack. Then it's going to, sorry about that, then it's going to copy init array to EIP. Okay, so I've got my return address here, and I start execution at this new place in memory. Okay, so that's what it looks like. But in order to make our code as reusable as possible, we'd like to build function libraries similar to those that we've used in C++. So we have to assemble the function definitions in a separate file if we want to do that. And if we do that, there are a couple of extra steps. Not a big deal. But we've got to assemble the procedure so that their names are visible outside of the file containing them. And then we've got to let the calling program know the necessary information about the external procedures. And then we've got to link the object files together to get an executable program. Now, that last part is something that we have been letting C++ handle for us. We'll continue to do that. I may show you how to do that at the command line, but we'll see how fast we go here. So let me show you what this is going to look like, okay? So, first thing, I've got a new directive, and it is public. The public directive is used to make procedure names visible outside the file containing them. So let's say I've got a file that has 2 procedures, procedure 1 and procedure 2. Okay, so I will put this in the file that contains the function definitions. This gives them global scope, or scope, not global, scope outside of the file. Second thing I have to do is I've got to use extrn, the extern directive. Gives the calling program information about these external symbols. So extern, I've got to say, okay, well, procedure 1 is, oh, that's a near 32 procedure. And, oh, procedure 2, yeah, it's also a near 32 procedure. Okay, so that's got to go in, this has got to go in the calling code. Think of this in the same way as a function prototype. Okay, so let me show you what this actually looks like. In the file with the function definitions, you'll see the public directive for procedure 1. Okay, this gives this identifier scope outside of the file. Here's the definition itself, okay? And then in the calling code, I want to call this. So before I get to my starting point in this piece of code, I've got to have my prototype, something that defines these symbols that I'm going to be using right here. So extern, this means, okay, there's an externally scoped procedure in our case that has these attributes, and that way I know about it. I have encountered it. It is seen in the symbol table before I begin execution here and march down to here and encounter that symbol. Okay? So that's what I have to do if I'm doing this in all assembly language, and this is how I would store the function definitions separate from the code that calls them. Okay? All right, that's it. We are done